In this video I will walk you through our tool and the 6 main tasks using a usage scenario about a heterogeneous dataset that is currently loaded. I will walk you through the interface using this heterogeneous dataset collection in our usage scenario, and what I would do as a very first thing is to filter some datasets out because the value domains of several measures are totally dictated by individual values that are produced by individual datasets. You can see it, for example, here, where individual datasets fully allocate almost the entire value domain for one measure and make this measure not useful anymore. What you can see here is that this selected dataset is the uneven density dataset. It's a nice one, but it's also one that is very difficult for some of our separation measures that we are currently analyzing. I will filter this dataset as it makes several measures not useful. The situation got a bit better. I will continue this for more datasets which seem to cause problems for several measures, including this one. And that one in particular, I want to see what that is. Okay, this is a dataset that is not separable at all. So this is a very difficult one where class separation should be very low. I will start with one of the goals that we had in our tool to find out if the orientation of the value domain is right, the valence, meaning that if the value is high, the separation is also high, or the other way around. And in this case, this particular measure produced a high value, but the dataset was not separable at all. So it seems that the inversion that I clicked here is wrong. It seems that this separation measure is not inverted. So I will click this button and then the inversion is taken away. I have now reached a state that is more satisfying. The measures seem more useful now. What I see now is that there is still very much variance going on and inconsistency between different measures. And what I would like to do next is to order these measures to get a more ordered visual interface and taking the maximum out of parallel coordinates. To do so, I use the list-based interface on the left. I click a measure that I would like to reorder, drag it to the right position, and then I re-include all the measures again. What I just did is to assign average between to the very end of this list, because I have the idea to order the measures according to their value distribution. Now I'm happy with the new ordering of separation measures. And I would like to proceed to the next task that I have in mind, which is to filter away datasets which have exceptional data characteristics. And my goal is to get more control over the dataset collection that I'm currently actually using. For that means I'm looking in the 7 interfaces that I have to do this. And I can see the distribution of all the dataset sizes that are currently used in this scenario. I can also select datasets by particular data characteristics such as the dataset size. And what I see here is that there are some datasets that are particularly large compared to all the other ones, and I will decide to use a filter. You can see here that the filter is propagated to the entire system. And I will reduce the number of datasets a bit just to reduce these outlier datasets. I will do the same for the number of dimensions, and I will reduce the dimensionality to about 100. Same with class counts, class size variation. There are 2 which are not filtered out yet. The skewness is an interesting characteristic, which is a bipolar scale, so I will only reduce this one here. Maybe I'll look at it. It's a dataset that has 6 dimensions, and it's pretty tough to assign a separation here. This is why most measures have quite low values, and I will filter this one out just by dragging the slider here. There are 56 datasets left, and currently 0 datasets selected. I can change this, for example, by, as you saw, selecting datasets here. I can select datasets everywhere in the visual interface to partition datasets into, in this case, 2 different bins. What you can see here is exactly this, a partition of datasets into datasets with small sizes and large sizes, and the binning is interactively steerable. And according to the main themes, how binning can be done, it's either domain preserving or frequency preserving. And in order to achieve more balanced distributions, I will choose the frequency preserving strategy with 2 bins. What I can also do is now to use this partition of the dataset by the dataset size to compare these different collections and see if there are differences in the measures. Because if so, we would be able to make an assumption that a particular value of a separation measure may result from dataset characteristics. And this brings me to the interface on the right side, where you can actually see for every measure these 2 different bins that I just created here. It's the same ones, and you can see that for average within all the measure values are very, very high for both cases, for both bins. You can also see that the most measures are located here. This is exactly the same. Ball the same. Davis Baldwin is the next one in our ordered set of separation measures, and for datasets with a low number of dataset size and a high number of dataset size, the measures behave almost equally. Same for distance consistency, and I can extrapolate this. It's almost the same for every measure. But interestingly, this is not always the case. There is one dataset characteristics which is quite interesting, and this is the characteristics if a dataset was a real world or synthetical dataset. And if I partition the dataset collection, then this binning is active, and then you can see that the distributions of dataset sets in these separation measures is quite different. All the datasets that come from real world seem to have lower values here, whereas all the synthetic datasets have higher values here, and this observation is the same here. It's the same here and again and again. Also in the silhouette measure, real world datasets seem to produce lower separation scores than synthetic ones, at least given the dataset collection that I'm currently using. In my analysis workflow, I would now like to proceed to the next task, which brings me to the interface on the lower left. It's the comparison of measures for ND and 2D data representations used, given that dimensionality reduction is used. For that purpose, I will reduce some of the measures which did not perform that well, because the value domains still seem to be quite violated by outliers. These measures seem to be a bit more robust and the distributions more normal. And what I will do is to now focus on 4 different dimensionality reductions and to analyze if the consistency between the high dimensional dataset and the low dimensional dataset is represented using particular measures. For example, if I use PTB serial as an example, you see that there are a lot of horizontal lines going on, meaning that datasets are assessed in ND as well as in 2D almost equally, almost no rank changes between the rankings of this measure, and this assesses that PT serial is quite useful if you want to combine it with dimensionality reduction. But however, there are other cases such as the normalized Hubert statistics. Here is a lot of rank changes going on. There is even opposed behavior, What I take away from this is that using normalized Hubert, just using this as an example, is not the best strategy when it comes to dimensionality reductions being used in such a scenario. I want to proceed and come to our next task, which is realized in the lower right interface. It's the comparison of different DR-reduced datasets using the same measures. What you can see, for example, using the Zeppelzauer measure is that the distribution for PCA, MDS, TSNE, and UMAP is quite nicely distributed right at the center of the value domain. There's not that much variation going on, even if TSNE produces a bit less high separation scores than UMAP does. PT serial shows a quite similar pattern. Also, EMS class separation shows a similar pattern, even if all the separation scores are a bit higher or distributed to the top of the scale. Whereas other measures are literally, ranked all at the top or all at the bottom. What I can also see is that some measures are quite outlier vulnerable. This is an observation that I already made in this interface. I can see this here again. For example, looking at the normalized Hubert statistics again, there seems to be one outlier in the MDS case, which dictates the whole value domain of all 4 comparison measures. After having done comparisons across different aspects, having compared and filtered and selected data sets, I would now like to use all these findings and observations to come up with a recommendation of a separation measure that may be most useful for downstream tasks given the situation that we have created with the data set. And given all these findings about data sets and measures, it seems to me that it's not advisable to use the measures which value domains are quite high or quite low. It seems to me that separation measures where the distribution of values is quite at the center, even following a normal distribution, seems to be quite useful. I have also seen that for the consistency between n-dimensional and 2-dimensional data, EMS class separation silhouette and PT serial have proven to be quite robust. And I also saw the same pattern here in the comparison of 2D representations, which helped me a lot to select one of these measures for either downstream task that I have. And this concludes the usage scenario about the heterogeneous dataset collection using our tool.